Welcome back to another Kempner seminar. Today, I'm very excited to introduce Dr. Nanthia. Nanthia Suthana. I was going to read her many interdisciplinary roles. So Nanthia comes from UCLA. She's actually in a very exciting transition, moving from UCLA to Duke, and will be joining us on the East Coast. Welcome to the winter. A gentle introduction. Nanthia's work spans many different disciplines, and it's a great fit for the Kempner integration of neuroscience and natural intelligence and artificial intelligence. And so her work spans psychiatry, neurosurgery, bioengineering, and psychology, and she focuses on developing invasive and non-invasive methodologies to understand and restore learning and memory function in humans. She has an impressive array of publications, which we'll talk about and hear many about many of her different projects. And she's had a number of major research grant awards and as well as postdoctoral mentoring awards, and has made major contributions to diversity and encouraging underrepresented women in STEM. And so let's welcome Nanthia.
Thanks, Patrick, for the introduction. Can you all hear me on the microphone? Or just
you can click out of that not hearing anything box.
Not hear anything box. Is that better? Does that eventually go away? Or? The top is not so important. Yeah, thanks for having me. This is quite an impressive place. Yeah, and I recently, moved to an hour-and-a-half long flight away, so that's exciting. And moving my lab in April to Duke, and very excited for many reasons. My work interfaces between, as was said, like sort of neuroscience, medicine, and engineering, and Duke happens to be very strong in all three of those. And I feel like the screen is blocking, but I'm gonna move a little bit. So yeah, I'm excited to start this next chapter. What really motivates my lab and what I think motivates most, or all of neuroscientists is how does the brain work during a complex experience such as this, right? So navigating a complex scene, lots of things are going on. There's other people. You're moving through this scene, and this sort of, perhaps not so unique, but unique to humans, at least, to direct a person to do this, is that we can mentally, experience these events, like replay them in our minds, go through them, think about past experiences, plan future ones. And sometimes, things can go wrong in the real world situation, but also in these mental states. Right? For instance, in Alzheimer's disease, where we have a hard time remembering these events, or in PTSD, where events that we don't want to really think about come about. And so the regions in the brain that happen to be very important for this are in the medial temporal lobe. It's a very deep structure, sort of if you went into the ears in the middle of the brain, two sides. And they're relevant in terms of they're first affected, for instance, in Alzheimer's disease, the hippocampus is first affected early on, which affects millions of people and has, huge worldwide costs. And in post-traumatic stress disorder, one of those structures implicated is the amygdala, which sits a few millimeters, away from the hippocampus, is also affected. And these are the areas that I'll focus on today. But of course, there's a whole network of brain areas that are, relevant here. And I mentioned those areas because they're very difficult to image or record from traditionally in human neuroscience studies while people are moving. So the technologies that we have to record from these regions, they traditionally require people to lay down, sit very still, and watch, a screen of stimuli. There are some techniques, however, that allow for some mobility, but those techniques are unable to record, these signals from deep brain regions like the amygdala and hippocampus. Now, in some cases, we can get direct recordings through electrodes that are implanted in patient populations that have to get neurosurgical implantations for various reasons. And so in those cases, you can even record single cells from these regions. But again, there are wires that are connected to a big amplifier, so you can't have these people move around. So they require immobility, and they when they do allow for some mobility, they record from superficial brain areas. And you are also limited often to unnatural tasks, that are like pictures on a screen rather than these experiences that I showed you in the video of somebody walking through a very complex. So my lab tries to move outside of the lab into more naturalistic settings with the opportunity that was afforded in 2013, which was the first device to be FDA approved to be implanted into human patients that can record brain activity. So before this year, the devices that are implanted into human patients were stimulation only, meaning they can only modulate brain activity, they couldn't record. So in 2013, I was a postdoc about to be faculty, and I saw this and I was like, oh my gosh, this is gonna change everything, right? And I thought everybody's gonna run to do this. And sure enough, that didn't happen because it's really, really hard. So I started my lab in 2015 and basically funneled all my startup to this new thing that I had never done before, which is to work with these patients, which now there's about 5,000 of them in the US. They have implants predominantly for epilepsy, to record seizures, to try to prevent those seizures by stimulating electrically into the seizure area. And so there are many, many individuals. Boston is a hub for many of these people who are walking around and you wouldn't even know that they have these devices implanted in their brain. So this is one of those patients who came to our lab. Now in the lab setting, we equip them with a lot of wearables. And we use motion capture. You see these little reflective markers that are being tracked by cameras on the wall. You can also put mobile scalp EEG headsets on them because the device is fully implanted and shielded. They can wear other biometric sensors for heart rate, for skin conductance, for respiration. You can put eye trackers on them. You can also put headsets on them to simulate the world, such as using virtual reality or augmented reality, which just adds stimuli to the world. You can use audio-video recordings. You can even take them outside and use non-camera-based or IMU-based motion tracking. So this field of wearable technologies is accelerating at a huge rate, as is the neural implant technology. And those two areas have a very interesting intersection, and that's what I want to try to share with you about today. So here's an example recording from one of our participants. They have electrodes in the hippocampus. Remember, that's the brain area that is very critical for memory. In fact, if you have damage to the bilateral hippocampi, you cannot learn about new personal events, right? So you cannot remember new episodic or autobiographical memories. So there's a patient with electrodes, 4 contacts in the hippocampus, and we can record between pairs of these. And what you'll see on the bottom right is a recording from 4 channels, bilateral hippocampus. On the left, you see their position in the room from the motion trackers and the eye movements from a wearable eye tracker, as well as their gaze position shown by the yellow circle. So we can record all this wirelessly as we are standing outside of the room. So we're watching from outside of the room. The participant is wearing this backpack that holds the equipment that allows us to, basically wirelessly stream this data, store it, and view it, and also communicate with it in terms of inserting little marks so we can mark the events across the data stream. Okay, so the very first study we did with this is just to simply watch and record while people are walking. That had surprisingly never been done. We've never recorded as a field from the hippocampus while people are walking. So what did we find? We found something that we've now replicated in every single study that we've run in the lab, which is that there are these certain wave patterns in the hippocampus that happen around 4 to 10 times per second. And you see one boxed in orange. And these are called theta oscillations. And they happen in bouts, meaning they're not continuously happening. They come and they go, they come and they go, which is very different from what we know about freely moving animal studies. If you put an electrode in this brain region in a mouse or a rat, and they start running, you see theta dominating the whole signal. So we were very surprised to see that's not the case, but I hope that I can explain to you maybe why that is. So they come in bouts. They're only present about 10 to 20% of the time, which is very low considering in rats they're there 80% of the time. But there are certain cognitive or behavioral conditions that will change the prevalence of those bouts. For instance, if you have somebody walk faster versus slower, just back and forth, they happen more often. Even if they're walking in a circle, if they walk faster or slower, there's a harmonic that has to do with the asymmetry of these waves, so they have interesting properties. But the first finding was essentially that as you walk faster, you see these more often than when you walk slower. Okay, but what about during a memory task? So asking somebody to simply walk back and forth, there's no memory demand. They could be thinking about who knows what, right? They could be thinking about what they had for breakfast this morning, or what they're going to do later. So we decided to embed a memory demand onto the task. It's still a walking task. So what you see here is a person walking, and we have them memorize a certain maze structure. So we have them look at this, this maze on a tablet, and we ask them to walk a path that looks like this. And so you can see in each trace a single walking path. Sometimes they deviate, but overall they're able to learn this path pretty well, such that the average of their, each participant is shown with the group, is very close to the actual maze. Participant 2, I realize Zoom can't see me pointing, but participant 2 adds a little extra turn right here, if you see. For whatever reason, they just wanted to do that extra turn, and we were initially frustrated by that, but then you just let them do what they want to do, and it ended up being very interesting because I'll show you the results from that little extra. Okay, so they're able to do this task. We're tracking them. There's a treadmill in the middle of the room, which we ask them to walk, and we try to match the speed according to how they actually walk through the real world. And we ask them to do certain trials where just walk, think about whatever you want. Later on, we might ask them, imagine the rightward trajectory, imagine the leftward. So mentally traversing this path in your mind. What we found was really quite striking. When you look at the maze and you superimpose theta activity onto this maze, you see peaks. And you can probably already see by eye that these peaks are happening around the turn. Even participant 2 right here, who added that extra turn, ended up being useful because you also see this peak. So these theta bouts are happening right before the turns, consistently across trials and across participants, which often in science doesn't always happen with human studies. And just to convince you even further, I'd like to show you some single trials, right? So this is just raw data, not, nothing fancy done to it. You're going to see the data on the bottom right here. Here you have a theta bout, and then they turn. Again, theta bout, turn. Happening right before they turn. I think there's a couple more right here. About 2 to 3 cycles, so a few seconds before the turn. And this is one example channel. However, each electrode, even though it's in similar brain areas across people, has a slightly different time course, meaning one might be a half a second earlier than another. And that becomes very useful when you take all this information together and, for instance, try to decode their position. So that's what we tried to do, is decode their position based on the nuances and the temporal aspects of the signal across channels. And you're able to do this quite well. So if you look at the actual position compared to an estimated position, and this is using just a very simple statistical model, you see correspondence. And the difference between the actual and estimated position, the errors cluster around 0. And so you're able to do quite well estimating their position within these segments just based on this signal, this neural activity in the hippocampus. Now, what about during the mental navigation? So again, they're walking on the treadmill right here, and they're imagining the routes. And then we have a control condition, which had happened before we gave them this instruction, where they're just navigating. They're just walking, and we don't really have any, they don't have any control over what they're thinking about. What you see is when you, plot the activity across the real world maze, you see some peaks that show some similar properties, meaning that they have, time courses where there are sort of 4 peaks. And if you look at the correlation across trials in the imagination or mental navigation condition, you see significant correlation as you do in the real world, but you don't see that in the control, suggesting that there's some shared, dynamics here in the signal between mental navigation and real world navigation. And it turns out that the hippocampus, as opposed to other areas like maybe entorhinal cortex or temporal cortex, shows the highest correspondence between mental navigation and real world navigation in terms of those correlation coefficients. Okay, there's a lot more going on in this paper. It will be out soon. We just got the proofs today. So, I can expand on this. We did a lot of other things like looking at eye movements, and there's a lot of interesting things that we found. So this task was not too difficult. The participants could learn it quite well. The next task was a little bit harder, and so we could look at incorrect trials when they're not doing, you know, what they're supposed to be doing. And this task was, instead of learning a maze, they had to learn particular targets of objects that are these halo cylinders in a room. So this is looking at the encoding. It's a virtual reality task. During retrieval, they walk through and they have to press a button on the joystick every time they're at, let's say, the red halo, the yellow halo, and so on. So there's no visual, you know, object. They're just doing this from memory. After they press the button, it does pop up and they get some feedback. There's also some control trials called arrow trials where they simply walk to it. And you can see they did pretty well on that one. Their button press was very close to the actual location of the red target. This trial, their button press was a little further off, so we would call that an incorrect trial. And when you look at the correct trials versus the incorrect trials, you see that this power signal, you know, peaks or increases in this theta band, you know, sort of 6 to 8 hertz, more so for correct compared to incorrect trials. Not the case for the visible feedback, and not the case for the arrow control trials. The time course of this is happening a little bit before the button press. So they're arriving at the target and it's happening about a second or two before arrival. Turns are not relevant in this task in terms of relationship to this. So this is quite interesting because the previous study I showed you, you might, you know, it might be easy to say, oh, it's just mapping out turns or something, right? But it's not the case. So turns in this task, which are not relevant to the task, turning, when to turn in this task is not important. It's where these objects are in the room. So this signal is mapping out those objects, meaning it's peaking around the positions of those objects. If you switch to a completely different room with different placement of objects, it remaps, right? So it's within a couple minutes completely changing its representation to a new environment. So these signals, they're dynamic. They're seem to be modulated by the goal, the memory task or the goal at hand, and they seem to be modulated by performance, meaning if they're doing better, you see them versus if they're doing. You can also put all of these things into like a linear mixed model and see which variable, speed, acceleration, eye movements, head orientation, head movements, position, you can see which one of those variables explains the most variance in the fluctuation of this signal, and you see that performance, you know, sort of takes the lead here rather than speed. Remember that first study I told you, it cared about speed, but there was no cognitive memory demand there. The second study, it cared about turns. That was very relevant to the task. And here, it cares about these object locations, which is important to that task. Now, here's the last task I'll show you before I shift gears a little bit. In this task, it turns out the walls, the position, the walls were very important. This room was our first lab. It was smaller. We upgraded a bit on the last study. It's a small room. When you're in a small room, the walls end up being very important for how you are sort of anchoring yourself where you are in that room. So if you do a spatial memory task in a small room, you know, the walls become very important. And so this was also a memory task in a room. You did have stimuli on the walls. And so what we found in this task is that when people were doing the actual walking, the signal would peak when they would get closer to the wall. So it was linearly modulated by distance to the wall. And I'll show you an example of that here. So as the participant gets closer to the wall, you see an increase in theta. And as they go away, it goes down. Matthias, who was a postdoc at the time, he's now just started his lab down the street from you guys at Boston University. He thought, well, what if we had them also sit in the corner of the room and watch me walk around? Do you think that these signals, which we don't normally think of the hippocampus as a social structure, but there were some studies in bats recently and I think rodents around this time that suggested that cells that responded to an animal's position also responded to other animal position. We thought, well, what if we have them sit in the corner and watch Matthias walk? Will the signals also similarly be modulated by the other position? And that's what happened. So here, as Matthias gets closer to the wall, it increases. As he walks away from the wall, it goes down. And this is just an example trial from one participant, but when you look at all the channels across the different participants, you see consistency here, such that they are modulated and increased by proximity to boundary versus inner area There's a lot more that went on into this paper, but I just wanted to give you one message, which is that here the walls we think are more relevant to this task and they're modulating, but that this signal can be modulated by another person's position. By the way, in that task, when they're sitting in the corner, the instruction was for them to pay attention to the other person's position, press a button on a keyboard every time they crossed one of those relevant locations. Okay, and then lastly, we took people outside. UCLA, if you've ever been to UCLA, South Campus, which is like the medical science side of campus, is really confusing. Gabrielle, I know you know how confusing NPI is, the building. So we did this study in NPI and the outer areas of NPI. I worked there for 20 plus years. I still can get lost in that building. And it used to be a psychiatric hospital, and people joke that it was purposely made this way so people, patients couldn't find their ways out, which is kind of dark. But this is the trajectory they took. It's a very convoluted trajectory. The goal was to learn the trajectory. So here, turns are important. They had to learn when to turn, where to turn, what doorways to go through. And they did this for hours in a day. Okay, we have, I think, probably close to 1,000 hours of footage recording these individuals. We did eye tracking, audio, video, et cetera. We found that across, a subset, actually this is all the data. So every data point is a single channel. Yeah, question?
So in the previous slide, how much do you think the background of the participant would impact whether the signal rises or not? So for example, like if someone is not used to being super social, would they still view someone as the same as someone who is used to being social?
That's a great question. I don't have any evidence for this because we didn't manipulate that, but I do think that sort of how actively you are, motivated to care about this person's position will modulate this, right? So you could think of an experiment to test that, right? Which we didn't do, but so this just sort of my hand wave. But I think that yes, it's relevant what they are trying to accomplish. What's the goal of the task? And maybe there are individual differences in terms of how much they care about other people. I don't know. Does the hippocampus care about that? I don't know. Maybe less likely than other areas like prefrontal cortex, but it's a great question. Okay, so all of the channels except for a couple, one thing we noticed right away is that this theta activity was much stronger when they were outside. So something about just going outside, and this is where we need computer vision and AI to tease apart, what is it about outside? Are they making more eye movements to just a larger space, right? Going from a small hallway to a large space, potentially more stimuli going on, potentially changes in arousal, who knows, So we measure as many things as we can in terms of arousal and luminance and so on, but just as far as the description of this finding goes is that it was just stronger outside compared to indoors. And we do see this turn-related activity such that it increases right before they make that turn and then drops really, quickly down actually below baseline after they make that turn. There are also a lot of interesting moments I'm not showing you here today, like when they get lost. All of a sudden they're like, where do we go? We see some interesting things there, or if somebody's talking to them, or, there's a lot of things you can do in these kinds of natural paradigms. So just to summarize the first half here, we find that in the hippocampus, and a lot of cases this is also entorhinal cortex, that theta activity increases in the form of these infrequent bouts. They're modulated by speed when the memory demand is low. When the memory demand is high, they are increased during successful moments of recall and at key retrieval points, such as turns, if the turns are relevant to their memory. They can be internally generated, as in the case of imagining navigation, where the external environment is not changing. They are dynamic, right? Minute-to-minute changes, environmental changes, contextual changes can change these representations, and they increase in outdoor environment. And then lastly, they can be triggered or modulated by the behavior of. Any questions before I switch gears? Yeah, no, because it's a good point. It's a good point to switch. Okay.
What, in your view, is the concept of what data is doing that ties together really?
Yeah, interesting. I mean, this is all coming. There's a lot of research on theta. It's sort of been studied it's been studied for decades. And, so the finding when you look at literature is that it's helping sort of create a sort of temporal structure for something that is important, we think is important for memory, which is spike timing. And spike timing dependent plasticity, to be more specific, so the timing of cells firing are locked to particular phases of this wave. If you block this wave, like pharmacologically, or damage a certain part of the brain that completely abolishes it, an animal has trouble like learning, remembering. So it's clearly implicated in doing something here. In terms of this, it's much more highly modulated and dynamic than what you would expect by looking at rat studies. And actually, when we first started coming out with this work, it was heavily criticized because it didn't make sense when you look at the rat literature. They started to look at freely moving monkey work, and it seems to be similar there. Even bats, other species, do not have continuous theta. They have them in these bouts, and heavily modulated by behavior. So I think what's going on here, and it's not that humans are hippocampus completely different than in rats. I don't think that's the case. I think that our cognitive state and behavioral fluctuations in the tasks that we do are very different, and which is why I'm so interested in moving outside of the lab and getting a little more complex, right? So if we just keep sticking to these traditional stimuli-driven memory tasks, we wouldn't necessarily understand what's really going on and how dynamic these signals are. So I think that this fluctuating nature of theta, the long answer to this, it is creating this kind of sort of temporal structure for the potentially spike time across populations.
Do you think it can basically be boiled down to kind of increased salience that things that you might want to remember?
Yeah, very, very important question. I mean, it's hard to answer at this point because we haven't manipulated it properly in terms of looking at the salience and the attentional, and it's hard to disentangle those two things. But my sort of gut reaction to that question is that there's something to that. So I'll show you a little bit later some data that suggests that, and actually in the outdoor data, that event boundaries are very critical for modulating. All these things could just very well be events, and action-driven, goal-relevant events. So, which are more so that may very well come here and so here. Yeah.
So there's also shockwave ripple. So when you see this, or imagine in the key memory moments, do you also see ripple events on?
Yeah, this is a great question. I think we're going to start to try to look in this now. I've been avoiding looking at that for one reason, for a couple of reasons. These are all epilepsy patients. And so, right, because they get the implant for epilepsy. Right? And we have thousands of them. We have 300 in the local California area that we recruit from. So we can select ones that don't have a lot of these epilepsy events. But sometimes those high frequency epilepsy events can look very much like ripples. And so I kind of just haven't looked, because of that confound, I haven't looked so much of it. But I don't think you can, I think you can investigate them. The other challenge is this device, for battery reasons, has a low sampling rate. It's 250. So you can look at about, and for other reasons, you can really only go up to about 70 hertz in the old device, 90 hertz in the newer device. And for ripples, it's not so great.
The question would be, so in those spatial imagining tasks for human, the theta also comes and go in the form of doubts.
Yeah.
And in your understanding, how does that relate to the event boundary in imagining? I can understand, like, if I go close to a wall, then this can be an event boundary modulated by theta. If I'm about to turn right or left, that can be, for my brain, that can be an event boundary. That would modulate by theta. What about imagination?
Yeah.
What's the event boundary for imagination?
I mean, it may very well be the same. I don't know. This is imagination is a very hard thing, or mental, it's a very hard thing to study because you also don't have like ground truth of thinking about it. And when we imagine, we also do a couple interesting things, is that we compress the experience naturally, right? We don't use the same time course. It's sped up, right? And we do jump around, right? In a task like this where the turns are sort of the relevant feature, if you imagine yourself doing it, you could just be remembering the turns, So the answer to this question is, I think they do still serve as some sort of mental event boundary, meaning they're relevant to this task. what we did in this study is we kind of enforced that they try to imagine slowly. So if they were going too fast, they take your time. We really want you to try to imagine at the pace at which you were walking. And so they would do a little bit better job at that. And so when you look across all the trials, I showed you that they are correlated across trials, but you also see some peaks, and you tend to see 4 peaks, in terms of these bouts. But I guess I'm not totally answering your question, which is, do those serve as event bound in magic? I don't really know. Maybe. Yeah, I have to think about that a little more if it's okay. Yeah.
This is all really fascinating. I'm trying to figure out how to separate attention from memory, because I feel like I was thinking, what does everything have in common? And I feel like it's when you're attending. Like when you're about to make a turn, you have to be, oh my gosh, remember, I'm going to make a turn. Even when you imagine, I think mental navigation, I think they have to also remember.
But okay, great question. But if I just put a stimulus, like those arrows, I don't know if you saw it, it was very fast, but there were just some arrows that popped up and I asked you to walk. So I just popped up a walk to it. The instruction is walk to this object that appeared. You are attending to that object. You make an orienting response and you walk. You don't see these.
I guess I guess it depends. I don't know. I was thinking about the walls. Like you're attending that you're gonna walk towards the wall.
Yeah.
And the bounce increases, right?
But what I didn't explain, and this is because I went fast. You don't see it if the task is simply walk to a stimulus. So there were all those little papers on the wall. If I just said walk to blue paper number 2, the wall does not modulate. It's only when I ask you to remember these target locations that you had learned in a previous learning task. I forced you to memorize certain locations in the room that were important, and I gave you feedback and I said, yes, that's the location. We had a Bluetooth speaker. Yes, that's the location. So later in memory, when I asked you to go back to those locations, so I'm going to this location right here. I might be walking over here. It's increasing when I'm getting closer to the wall. Only when I'm actively searching for this thing in my memory. If I'm simply just walking to an object and I'm getting close to the wall, it doesn't. So it can't be just some sort of, non-memory related directed attention. Does that make sense?
Thank you.
So for the folks that were watching people walk as well, they had just completed the task and they had
just completed the task, and there's a smart way Matthias did this.
Yeah.
So he looked at the periods when they were paying attention to the person and trying to answer the question, are they crossing that relevant object? Like not relevant object, but position, that's important. You see the wall effects when they're doing that, but right after they press the button, when they're presumably not really caring about their position relative to the target position, you don't see it. So he also was able to show that in the watching condition, it was only there when this memory process was being engaged. It's a I recommend reading it. He did a lot of, that's why he got so many job offers. He did a great job with that, several conditions. So it's not just simply the wall. It's not simply the turn. It's not, simply the object. It's the cognitive process that's being engaged. One more question, yeah, I'll take, and then I'll go to the end. Okay, so here and then here. Okay.
So you saw similar things for the internet.
Yeah, in this study, yeah. In that study, no, but I don't know that we had enough electrodes to really parse out if there were nuanced differences. I also want to mention we saw lots of interesting thing in the higher frequencies, gamma. Gamma was locked to the signal. If those of you are really, neurophysiological connoisseurs, and it was coupled in such a way that the amplitude of gamma locked particular phases of theta, which is something that's studied quite. But topic, yeah.
Did they try to imagine the path before they actually tried?
Yes. Well, so this was an interleaved design, so they would walk and then imagine and walk and imagine. We did manipulate it such that, okay, we alternated left and right. So you just walked right. Now I want you to imagine left. Now you walk left, now imagine right. And then we also did imagine what you just did versus imagine what you're going to do next. We did all sorts of manipulation. Nothing was really coming out in those manipulations, so it's not super exciting. But we're recording a field signal. So we're now doing these studies with single cell recordings, and it may very well be that the single cells may have information that parses those differently. Okay, so I want to shift gears a little bit, but it is connected. So when you think about PTSD, you can think about it in sort of two different ways. You can think about it as anxiety disorder, right? This hypervigilance and hyperanxiety. You can also think about it as a memory disorder, right? Because there are these events that certain patients, they have flashbacks, and they're so debilitating to the point where they can pass out from remembering these very traumatic events. The hippocampus and the amygdala is also thought to be involved. So we wanted to study this with this platform. And the way we did it was to have people walk around with VR and scare them, essentially. So I'm warning you that this video, there's an aversive moment that happens. So I'm giving you a warning, so it might not be as effective. I have given this talk where I don't give the warning, and it was quite effective. But before I do that, I do have to change my sound here. Sorry. So the concept is this. What you're seeing is a video from the device, the same device, but used for epilepsy. So what it does is it monitors brain activity. There's an unusual signal detected, and then it triggers the stimulus, right? Monitors brain activity, unusual activity, turns on the stimulator. And so this is how we wanted to use this for PTSD, for these flashback events. Instead of using seizure-related activity, we're using amygdala theta activity. And the response is to stimulate in the electrodes that pair the hippocampus and the amygdala. So there's two contacts, and it's bipolar, and it's bilateral. This is the results from that first patient, Adam, who just shared with you his story. Okay, so what you see on the left in orange is the CAP score. This is the clinician-administered PTSD scale. This is how clinicians assess the severity of PTSD. The higher the number, the worse, right? All these patients, they start around 50 to 60s, which is very, very severe PTSD. And what you see is right about the month after the stimulator was turned on, a dramatic drop in this score. We also have PCL, which is a subjective score that's also dropping. The subcomponent of this score, there's a part called re-experiencing, where they constantly are re-experiencing their trauma. That's what's going down. And you see it's maintained over 3 years, okay? Adam's life, as you'll see in the next video, has changed because of this. He was able to go to Disneyland for the first time and watch the fireworks with his kids. And he'll explain to you what happened actually during that experience. Let him do that. Now, I just want to note the stimulation here. Stimulation, there's small 100 millisecond pulses that are happening, thousands of times per day, about 3,000 times per day, probably more than you would necessarily have flashbacks. But so it's really only about 90 minutes of day spread out throughout the day that is intervening. And it's sufficient enough to improve his outcome. Apologize. He rushed in to get away from the sounds. He started to feel hypervigilant and sweating. And he rushed into a store, to get away. And that's when he just sort of felt it was okay. And he went out and watched the entire. So, if you're interested in learning more about his story, he's actually going to give a congressional briefing on the 20th of this month to hopefully share with congressional members how important this kind of research is. Continue to support. This is all funded by the NIH. Okay, so this is patient number 2. Okay, so the improvement is not so dramatic, but it is slowly steadying. I actually have data out to now 40, and this patient is in remission as well. So remission is the cutoff dotted line, which below is like pretty much like you and I, right? So we're talking about single digits in this cap. And there's a couple of reasons why we think that it wasn't so fast with this patient. I think the most important one is you can see that the number of stimulation therapies is very gradually increasing compared to the previous. And one of the reasons for that was that the detection algorithm that was set to only stimulate if both sides were showing this. Versus the previous patient, it would turn on if either or. And so we quickly changed that in this one, and then it started to ramp up. There was a clinical reason to do that. They were worried about sort of overstimulation, but once they realized it wasn't overstimulating, they did change. Yeah.
Yeah, maybe you're going to get. Do you know if there's an effect on theta?
So, of course, I'm interested in that. There's a couple challenges, but I also will give you some good news. Bad news is that this device when it stimulates, there's sort of an amplifier saturation period where it shuts off. You can't record well. No.
You can't record what we're doing the other time.
You can. That's what we did. We also, so we did it in a different kind of way, which is that you also can look at like just provocation of theta. You try to provoke it in the lab, and we did that in different ways. We brought them in and we played their trauma for them. We exposed them. And in the beginning, you see that theta increase before the stimulator. After a few months, in the first patient, it's not provoking that signal as strong. You can also do like emotional cues, you know, and you also see the magnet swipes at home, these events that would normally be very debilitating. They're also not showing as much of it. So there are sort of different ways that are not like time locked to after the offset of stimulation, but that we think is sort of reflecting the probably neuroplastic changes that are happening in the system, longer lasting. And that also happened with patient 2, slower, right? Not right away, but I think in the 6-month period.
Can I ask one other question? So, you guys are looking at follow-up after you stop stimulating and whether
No, so they've been stimulated for 3 years.
and they're going to just keep getting stimulated indefinitely.
Yes.
And is there some idea that this high frequency stimulation is disrupting it, or you don't know?
We just went with what people use to disrupt, but there's so many parameters you can change here. You know, this is where the biophysicists come into play, but we didn't, you know, have the time. You know, this was just to try it out and see. I think we just really got lucky, but also the fact that this set of parameters work tells me that there is a lot of room in terms of how you can basically shut off this area, you know.
So the stimulation, I have a question about the stimulation. This is done by macro electrodes?
Macro electrodes are 1.5 millimeters in diameter, a few millimeters apart.
And this is done in the pathway from amygdala to this, or
So one electrode's in the posterior amygdala, one's in the anterior hippocampus, ventral if you're talking about rats. And it's also DTI guided, so they do DTI beforehand and look for the area that's highly connected to an area in the prefrontal cortex that is implicated in PTSD. So there's some thought about the target.
Oh yeah, there's another target which is SGACC.
That's the area that they were looking at the connectivity. This device can only implant 2 probes, and so if it could do 4, you know, you would probably want to go to those.
Right, and yeah. Very good. So what's the remission rate going to SGACC?
Well, right now we only have, you know, 2 patients who've completed the trial. 6 is total. We have 5 implants. 1 just very new. This is all like we just started. Nobody's implanting other regions. Nobody's doing PTSD in this way. So we don't know what the other region. You know, there's some TMS work on it, but we're dealing with memory flashbacks in PTSD is a very specific symptom of re-experiencing. You know, this in our hands seems to work well, but this is only a few.
One more question about biomarkers. So this amygdala theta, is it a leading biomarker to the flashback, to the conscious report of the flashback, or lagging biomarker?
That's a great. I mean, when they're doing the at-home recordings, the synchronization is not very good, right? So all they're doing is swiping, and then you get the history a little bit, right? So I don't know the answer to that question, but I have a way at the end of the talk that I think we can answer. So that's a great question. At this point, I don't.
And what about it?
But in the lab, sorry, one more thing. In the lab, if you provoke them and you remind them of their trauma, I mean, obviously this is happening after the cue, but in the spontaneous case where they're just, you know, externally cued or something's happening, I guess I just don't know yet.
What about timing relationship between amygdala and hippocampus?
Yeah, this is another technological challenge because you need another pair of electrodes to look at that. This is a pair between the amygdala and hippocampus, the bipolar recording. You cannot separate them. We just need yes, it's stimulated across the region. So do I know if it's amygdala stimulation, basolateral amygdala stimulation, or ventral hippocampus? I do not know the answer. All I know is this region seems to work. We're going to go with that. Yeah, those are all great questions. Like, this is what we want to understand.
At this point, how much pattern stimulation?
None has been tried. At the end of my talk, I will introduce a new device that we've built that can do any kind of pattern that you can stream of, any kind of AI embedded algorithm to detect and trigger. I mean, that's the future. That's what I would like to get to. But this very, very simple area under the curve calculation to trigger, it seems to be working, which is very exciting. But this first patient was the most dramatic. The other ones was not, as quick. So there's some improvement that we can make. Yeah, back there.
Sorry, I know.
I love questions. I don't like talking for an hour.
So I might have misunderstood or misheard you, but you were saying that these patients will continue to receive the treatment every time in perpetuity.
Yes, that's the hope.
So, but you also mentioned, again, maybe I misheard this, but that you note that the theta activity decreases in response.
Yes.
So is there some learning, some
Yes,
teaching going on?
that's a
Like
great
what
question. Oh, this is so perplexing. This is like one of the biggest mysteries. Because they're getting better, but the number of stimulation therapies is going up. And if we were to take it away, I don't know, but we don't want to take it away. They don't want it. So what's going on? Like, why does it keep triggering? So there's a couple of things we think. One, they're getting out more, right? They're getting triggered more. They're putting themselves into situations that are going to be a lot more triggering. That's one answer, potential answer. Another one I think has to do with plasticity. Something about the system is sort of learning that this is good for it or something, and it's maybe remapping. I don't know.
Laser therapy.
Yeah, I don't know.
Facilitator.
In order to do this, the next stage is you would have to do like a double-blinded crossover where you turn it off. I mean, it's very hard to do. These patients wouldn't want that. You see the time course changes. This was just a phase 1 safety trial. Is this safe to do? Very early stages. So that was patient 2. Patient 3, again, very slow sort of improvement, but steady. I will make just a comment of what I think, the first patient, their symptom of re-experiencing was the strongest out of all of them in terms of those flashback episodes being very vivid. Also had the strongest theta signal to any provocation made, but I don't know why that patient improved so quickly and so dramatically. Okay, so since we developed this platform, I would give talks and scientists, clinicians would come to me afterwards, like, can we use this for other things? And I'd say, yes, I would love to do that. So collaborators have used it for obsessive compulsive disorder. And they recently published in a patient that they were able to reduce compulsions in this patient by using a low frequency signal in the nucleus accumbens or ventrum. So that 3D device was implanted. We helped them with doing some experiments with eye tracking and introducing stimuli that were very provoking, like smelly rotten fish, and also built them a virtual reality. They've also done it for binge eating disorder, where they, in these patients who have loss of controlled eating, they would basically come to a buffet of food, of lots of bad food and good food, and they would eye track them and try to find the signal that would predict these loss of controlled episodes, and then they had a lot of. The one I just want to show you is this one, which is not published, because that's always, you can go read about the other ones, but this one, this is Parkinson's patients. So Parkinson's patients, they are usually implanted in the basal ganglia. So like striatum, subthalamic nucleus, globus pallidus, these areas, which, so there's like thousands of these patients. Yes.
Speak to the microphone, please.
Yes, the microphone's on my lapel, but it's not coming through. Hello? Oh, you know what? Maybe the volume? I could stay over here. Is there another microphone? No, here. When I move around, it gets worse, so I'll just stay. I don't know why the microphone works here. Okay, thanks. Okay. So these patients, this is an example of a patient, subthalamic nucleus electrode on the bottom, scalp EEG, one channel on the top. And what we did here is that we created a virtual reality paradigm to try to trigger freezing. Freezing episodes in Parkinson's are very debilitating. So for instance, getting to an elevator and not being able to move through, or a doorway, and so on. This is the lab right now at UCLA. And you see this barn door right here? We created a virtual version of that such that we can both in real world and in virtual world to compare, manipulate the opening of this doorway. As the patient walks through the doorway, there is a moment at which they freeze, right? And the smaller that opening, so they're okay going through now. They're going to turn around and go back. And as they go back, right here, you could see it. They're going to have a freezing episode right here where they shuffle a little bit their feet, and they can't go through. And the smaller the doorway, we're testing whether that is a trigger. There's a lot of other triggers you can do. We have a busy intersection of the street where people are walking and cars are coming and that sort of thing. Anyway, the goal is to predict when they're about to have these freezing episodes such that you can stimulate to prevent them from happening. This is very early, so I don't have any results really to show you, except that we have gotten this paradigm to work to test. Okay, and then am I out of time? I think so. A few minutes.
Yeah, flexibility.
Flexibility. Okay, cool. Because this is something I'm really excited about, and I told some of the trainees and people that, what are you most excited about right now? Yeah, it keeps going in and out. Maybe it's a battery issue, and it I can use the handheld. That was great.
There's a, yeah.
Okay, I'm gonna scream. This is what I'm excited about. Okay, I was at my son's birthday party. We did laser tag, and one of the parents was wearing these glasses. They're wearing these glasses. Hello, testing. And there was a little green light. Right? Hello. You guys can hear me though, right? If I scream. Okay. There's a green light on the glasses. I'm like, what are those glasses? Why is that green light on? And if you know what these are, they're taking video. They're taking audio, video. These are the Meta Ray-Ban glasses. When I saw this at the birthday party, I said two things. I was like, can you share that video with me for my son's birthday? I want to capture this memory. And number two, I can use this in my research. How do I use this in my research? Well, if I have these patients use the glasses and capture memories that they're creating out in the world multiple times, as many as they want, this is the first window into recording from the hippocampus while you form these personal autobiographical memories. We have never recorded from this region in humans when you make memories. We do it to recall memories, right? Or make artificial memories like things on a screen. But a rich, complex autobiographical experience like a birthday, right? We haven't been able to capture that. And so I thought this is what we can do. It took us a while to get there. This is a very clunky version, prototype 1.2 or something. But it's essentially an electromagnet that sits on a Velcro cap that when they push a button, inserts a little signal into the device to trigger storage a couple minutes back, and triggers an LED that you see on the glasses that is embedded into the camera. So you have a time sync signal between the camera and the implant. And they go and do this at home. This is a memory that the patient created. Now this memory, it doesn't have any people in it, just for patient privacy, but there's sound in it. He's describing basically the break room at his job on his last day of work and how much he's gonna miss this break room. And he's looking around, okay? So now if you just look at the first little bit of data that we have, we asked them to replay these videos on their phone, which is something we do all the time, right? We capture memories and then we watch them again and again and again. So we recorded while they replayed these videos, and there's this is brand new, like last week. So we haven't analyzed this really, but just by eye, there's some consistency across replays. And guess what happens right at that moment? The environment shifts to the other side of the room. It's really time locked to that contextual shift, maybe an event boundary, right? So this is just like a first look at this data. These are all the different types of memories that he's captured. Really, some interesting ones, like, Chinese New Year just happened, so there were a lot of, and his family's Chinese, and so there are a lot of interesting things there. There's a diversity of events and memories, and so one of the reasons I'm very interested in being here is not just because, AI can help us, predict psychiatric and neurologic events and forecast behavior. It can also help us make these devices smarter, right? When to stimulate, when to intervene. But this last one is that when you start to capture these very rich memories, replay events with maybe some aura rings and glasses and all sorts of things, you have this very rich data set that at a certain point, we are no longer going to be able to utilize. And so using computer vision on these video files, really parse out things that are happening in there, very interesting. There's also all sorts of new wearables that are coming out. We're developing a sweat sensor to measure cortisol and epinephrine. We're not my collaborators work with them. You know, this data set that we're creating is very rich. This is not even looking at all of it, right? This is just 14 minutes of neural activity, speed, fixation time, event segmentation that we could create by annotating it light. I mean, it's a very complex multimodal data set. Once we start recording single neurons, we get neuropixels into humans, which are these electrodes that can record thousands of neurons. What do we do? What do we do? And that future is not very far. In fact, we have been working for over a decade now with a collaborator who has built a new device that can record single units from patients who have microelectrodes implanted. And we did this while the person was walking. The device is implant scale, so can fit into like a small pill size device. It can also stimulate with like any kind of parameters you would safety wise for sure, but with an assortment of parameters, and also have embedded AI to these slides. Okay. And this is for Gabrielle. Pretty much this slide is just for you. This is our first patient that we used to record. To record, what we did is we, did screening. These are responses to certain stimuli in the hippocampus, single cells, and then we had them walk just outside the hospital room, either make a left or right down the hallway to remember associations of stimuli to certain parts of that trajectory. So it was sort of a Y maze, and they did this over and over again. And this is just one person, and literally just happened. One thing we noticed by eye is that when it's not always told, really like that doorway, and then some cells, really responded across the space, whether they're good cells or not. Oh, they were. Okay, all right. And that's it, just in time, get the microphone. Say the most important thing of my talk, which is, these are the brilliant people that did all this work. And I want you to pay attention to the diversity of individuals. I know that's turned into a bad word right now, but this group is the most diverse. I mean, not in just their expertise, right? Electrical engineers, psychologists, medical students, artists, biomedical engineers, we have it all. And also from different countries. I think there's like 8 different countries in this group, and cultures. And so this is, I think, where the magic happens in this kind of work, and really cannot be done without them. These are the folks that are agreed to move across the country with me and are planning to come along. And then, of course, we work with neurosurgeons, neurologists, industry, many, many people who make this work happen. So with that, thank you. And happy to take questions. We are recruiting at Duke, especially folks with expertise from a place like this, because that's my next 5 to 10 year plan and priority, is to capitalize on the complexity of this data and to really apply, AI and more advanced computational methods to parse information out of it that we may not otherwise see. Thank you so much. I'm happy to take questions.
Thank you so much. I was really wondering about the why 2 patients out of the 3 patients with PTSD, didn't have the scores. I noticed that it's a total score, so I was wondering if you probably looked into the types of categories that contribute to the score and see if maybe that's what's causing that.
So the first 2 patients are in remission. The third is actually about halfway there, which is pretty good for refractory PTSD, by the way. It doesn't change at all. The scores don't change with all sorts of treatment, right? So that's still good. Yes, we looked at the sub tests. In the first patient, pretty much all of them are getting better. But especially re-experiencing. And all of them do report, there's some things that you just get from their reports. They're not having nightmares. That's a huge benefit in these, right? So just that in alone, could be very interesting and effective. If you just reduce these flashbacks and nightmares, you may not be, helping as much their hypervigilance or their other anxiety or related issues, but if you can help their re-experiencing of these memory flashbacks. So it's really about which patients you recruit for this. I don't think if we go to the next stage, I don't think we would try to recruit very specific types of patients who have very debilitating flashbacks, right? And re-experiencing is the problem. For this approach, I think is the best. Here and then here. I have a rightward bias, so I will make sure to turn and look for hands over here. Go ahead.
We have a question on the results, which relation does he lose memory about his bad memories, or is just lost link of his memories to the
The anxiety response. Yeah, no, he hasn't lost, well, we'd have to do a little bit more digging on the description content of the memory, but I don't think that the content of the memory is gone. I do think it's sort of breaking up the connection between the memory and the fear response, or the hypervigilance anxiety related response. But this is sort of just the commenting. I think we need to dig in. If we were to now go in, it's hard, because in order to really answer that question, you have to do a complete assessment of the content of his memory when he recalls this memory, and do it repeatedly over time and see if that's changed. And it's very hard to get these patients to go through that, especially in the beginning. They don't want to go through that experience. In fact, some of them can't get through the whole thing before they dissociate. So anyway,
that's why you stimulated the two areas.
Yeah. I mean, I would love to tell you that we knew everything from the get-go and planned this all perfectly, but I think a lot of it just happened to be lucky. The surgeon collaborator I work with, he did do this in rats. Before we went to humans, we had some ideas that maybe this works. A lot of it we just didn't know it works. Okay, so I said somebody over here, and then I'm going to go to this.
Okay, so I missed the first 10 minutes of your talk, so I apologize for missing some of the details, but you were able to identify replay at was it at the single cell level within humans?
This was all at the theta sort of level.
At the theta. Yeah. Okay. So, I think that might answer my question, but that was upon retrieval, so it was retrieval initiated. Yeah. So do you anticipate then the next step being trying to identify, or have you been able to identify more incidental replay, right? Like more offline replay that isn't necessary?
We have a nap room in the UCLA sleep room with a Murphy bed, and Duke is building one for us now. So we've recorded many, I'd say 7 people who've done a memory task, and they take a 2-hour nap, and then they do it again. And we are recording during sleep. So we are testing somewhat related to this. It's challenging. There's some challenges with ripples and stuff and that kind of thing, but I am interested in that question. So maybe in a year or 2. Okay, so I went to you.
So going back to the observation for simulation over time, you mentioned 2 possible explanations, but is it also possible that there could be some new kind of adaptation where it's like the trauma is trying to really pressure and it's kind of related all of that.
Yeah, well, the battery does die about 8 years. So that needs to be planned. You can check the level and replace the battery. It's a cranial battery, so you can replace it without moving the electrode. So that is the plan. But yes, it could also break at some point. In fact, in some of the other psychiatric trials, they noticed some patients just got worse all of a sudden, and then they noticed, right, it's working. So, that's always a worry in these. There's a whole ethical component to doing it. But, at least so far, we haven't had any of those kinds of. It's something you really need to think about, plan for. So far so good. And in some of those studies actually took time, like months, for them to get worse. So I wonder if, some of that effects are a little bit longer lasting, but I mean, I don't know, we haven't tested any. I really see all of this as like a really very early preliminary, the title of the paper was pilot study. I mean, this is very early days, right? So, but I love these kinds of ideas and questions because, where do we go next? What do we answer? What kind of questions we answer? That's a great question. I don't have answers to that.
Very interested about the device, the 1.2 version that you showed. Can you explain a little bit more, like what it does, and also the specific why it's as wired in between?
Why it's wired? Why
yes.
it's wired? So this is the one that records single cells. Which device?
The Meta.
Oh, the glasses.
Yeah.
About that device? Oh, it's $200. You can go buy one. It's not ours. Oh, the one that we built. So we basically just, attached an LED to the frame and connect it by a wire to an electromagnet, which is essentially like a refrigerator magnet that we can induce a magnetic field. When we induce that magnetic field with the button, it inserts a little artifact in the signal, which this device happens to be triggered by that artifact to store data. And it does so in a way that it takes a couple minutes behind and a minute forward, or a little, So we saw this device and the limitations it has, and we built something that would work for this purpose. We are trying to build another one and hopefully build many so that you could have 5,000 people doing this, then they never even have to come to lab. I mean, what graduate student doesn't want all of their data being collected by people out in the world? It could be very interesting. So I guess your question is like, how does it work? Does that explain it?
Yeah, so the device that you showed, not neuroscientists.
Okay.
I'm wondering what it connects with the neural.
It doesn't connect. So it's just inducing a small magnetic field, which if you have electronics inside the brain, it's going to pick up those magnetic fields and you're going to see an artifact in the signal. And the artifact is very consistent. When you look at the data, you can clean it out. It's not a problem. And it also happens to be that this device was built to look for that artifact. When it sees it, it stores the data. Now, if you don't wirelessly transmit the data off, it'll overwrite itself. So the patient has to transfer the data at night. They take a little device, they put it on their head and wirelessly transmit the data to a computer, which goes to the cloud, and then we get the data. It's very complicated. It took us months to do this, right? But it works out, yeah.
How synchronized with the video signal be with the?
Yeah, so this is, it's about 125 milliseconds, which is not great, right? The other lab studies, we're talking like under 10 milliseconds. So it's not perfect, but I think it's still useful, especially for this low frequency signals. We're not looking at high frequency signals.
One of the patients described the experience of the simulation as sort of the feeling of water flowing over him. Did other patients describe similar feeling? Is there any hypothesis for where that feeling comes from? Yeah.
We haven't tested it. My gut, answer to this is that it's not something related to the neural, so in the beginning, when you put this device, you test a bunch of stimulations just to see if the person can feel it. And you go low enough to the point where they don't consciously detect or perceive the stimulation. You don't want that, right? So I don't think, in fact, if you stimulate the amygdala too high, they start to get hypervigilance, their heart starts racing and do all sorts of things you don't want. So we keep this very low. The current is very low. So I don't think it's something to do with the actual stimulation. I think it's, basically what we want, which is, and I'm biased, of course, is a change in this circuit, which basically in this circuit, if you kind of disrupt amygdala activity or amygdala hippocampal activity during this moment, it can't really do its thing in the network. And so you don't get that sort of automatic physiological response of heart racing and sweating and maybe leads to dissociation. But I don't know, right? So I think to answer that question, you have to just bring them in and test time block stimulation paradigms, get their report, and you can do this. You can do this. So we haven't done that. Yeah. Yes, it does.
So this
it triggers. It happens during sleep. In fact, in a couple of the patients, it's only happening majority of the time during the first couple hours of sleep. In that first patient, it's not. It's sort of distributed throughout the whole day.
They don't wake up.
They don't wake up, but here's the problem with this. We need better at-home wearables to really answer that question, right? So we did put Oura rings on all of them recently, and we haven't looked at this data because at this point, we don't really have a good way to know. They can mark down when they wake up. They can say, I woke up at 1:23 a.m. and then I can look, when did it stimulate? But it's a very messy thing to do. Like, I think what you want to do is yeah, I don't know how you would do this. It's just hard to answer that question. Yeah. But yes, you can look at how the stimulations are distributed across the day. And you do see that in a couple of the patients, they're really focused on that sleep. But they don't report any sleep disruptions. In fact, they report better sleep and less nightmares. And don't know. You can put strips that go on the cortex. Well, I mean, so that you can also detect, well, you can do scalp. So in the sleep study with the naps, we do scalp EEG to sleep stage. That's like one way to do it. At home with the PTSD patients, we haven't. We're now looking at whether the intracranial EEG, I mean, Yuval has done a lot of recordings in these regions to look at sleep. And there's a lot of relationships, to the scalp electrodes where you can actually sleep stage. The problem we discovered with this device, and now I'm going off on tangents, is that during sleep, the waves get really big. And if the setting is not set appropriately on the amplifier, it saturates the signal and you lose it. So during certain times of sleep, when we brought them into nap, we lost the signal because it's cutting it off. You can change the gain on the system. And once you do that, then it's fine. So I think a lot of data just ended up being unusable because of that. And also because, remember, this is a rolling buffer on this device. It overwrites itself. And you can't record continuously during sleep at home. I can record continuously during sleep in the lab, right? I bring them in, I put something physically on them. But if you were to do that at home, the battery would go down very quickly, right? There's a lot of trade-offs here. There's a lot more complexity to this is why nobody else really has done this kind of work, except for me and my 2 postdocs who are now starting their own labs. There's so much complication to it, but I try to convince people that it's worth it. And I'm willing to help other people do it, right? So in Boston, actually, you have someone who does this. He just started. He got his first patient last week. You know Matthias, right? You met him? Have you met Matthias already? Down the street, he's doing this. So I think that, when you have somebody close by doing it, it's much easier to do collaborations, and he's very willing to do collaboration. So I think those kinds of questions can be answered eventually, but there's just challenges you have to figure out.
I know you mentioned you can do
Yeah.
So actually, it's what's a systematic approach to develop in certain situations.
Yeah, I mean, a lot of that work, in fact, Duke has Warren Grill's lab at that, and Cameron McIntyre. A lot of that work is better done in biophysical models and animals. In a human, to map out that parameter space, and with the technology of implants that we have now, it's just not going to be a good. So I think the answers to that are going to come from more biophysical modeling, animal studies, understand what the stimulation is doing. Let's say it's to increase spike timing dependent theta relationships or something, or theta resetting, or there's some hypotheses that we can look at. If that's the case, then we translate it to humans. I think that's going to be the way forward on that. Yeah.
It's not personalization.
Not yet, no, because it's too big of a parameter. You have the frequency, you have the current, you have the pulse width, you have, so many parameters. You can do different shapes. So this device I showed you at the end can do any custom shape you want. But right now it's pretty much boxcar shapes, maybe sinusoidal, but that's not really, so there's very limitations. Sorry, hitting myself. Did you have a question?
Yeah. Process where you track eye movements, how technology do you use for that?
In the lab, we just use pupil labs. I like those the best because they're easy to use and cheap, and the data quality is good. So that's been our go-to.
So in most of these experiments, do you think if people were asked to sort of imagine, say, tracing a path and then in comparison to them actually doing it, do you think there will be any difference in the activity? Will it be sort of similar? Yeah. a difference if they were to imagine and then when they actually use the case of the.
Yeah, I mean, this recent paper that's coming out, it's really focused on the shared similarity, but there probably is differences. And I don't think that we fully understood what those are. So at the first step, we've noted that there are similarities, which I think is the first step. So yeah, I mean, I haven't thought too much about it. I think about it, what would be different? Maybe the time courses or the noise in the temporal course of the signal or other things. Good question. Yeah, go ahead. Can I take her first and then I'll take you after?
Yeah,
you have asked questions? Yeah, you first.
I was wondering, so the thing about happened a little bit before these moments, these like crucial moments in the task. Yeah. If you eliminate predictability in your task, I don't know, maybe you're in a virtual environment and then all of a sudden it changes, or you take away vision, or things like that. What happens to the information?
Haven't done it, but I think that's a great question. We do have a grant that hasn't been announced. It's a private foundation. On uncertainty, introducing uncertainty in navigation, and it's across species. So that'll be very interesting. What happens if you switch? What happens if you had teleportation poles, or you change the one-to-one sort of visual to, so, and then, you could also take away certain things like vestibular visual or movement and see what happens. So these are all great questions, and we haven't done it. But you can do those kinds of studies. Yeah, one last.
Yeah, so I feel like sometimes in the DNS literature, there's a talk of some excitatory versus inhibitory pulses. I think like maybe in the DBS and in the closed loop world as well. Is that just about, what does that mean? Is that about tweaking the parameters that have some, like, and how do they validate that?
That's a great question for if you didn't hear it. In the stimulation or neuromodulation literature, there's a lot of language about excitatory stimulation or inhibitory stimulation. And the truth is we don't really, at the end of the day, understand. But I think it has to do partly with where the electrode is. If it's in gray matter, for instance, and it's a highly inhibitory population of cells, that's going to be very different than if you're stimulating a white matter tract of axons that are excitatory on the downstream region, right? So my first answer is that I think, like if I were to do a stimulation experiment when I want to excite or enhance a particular area, I would go in the white matter between entorhinal and hippocampus. And then maybe I would change the parameters based on some of the literature, but it's a very limited literature there. And so I do rely on those people like Warren and Cameron, who are modeling it. But there is a whole field in that that's going to be very critical here. But the fact that you can just, and with the Parkinson's DBSs, you could just totally kind of disrupt, what we think we're doing is disrupting a nucleus, like a gray matter area, and have these very dramatic behavioral consequences of improvement, suggest that there is a way to do it in parallel while we're tweaking and optimizing the parameters and eventually getting towards enhancement. Why didn't we go with the enhancement experiments first? Because those are just much harder. Right? So, but I am interested in that as well. Amazing questions. Bravo. Great questions. Thank you.